Hi everyone. In this video, I'm going to talk about what you'll actually be doing in Lab 3. So the main circuit that you'll be building in this lab is what's known as a frequency discriminator. Now, a frequency discriminator is a system that converts a signal x of t equals cosine of omega ct plus phi of t into omega c plus d phi of t dt. So it converts the instantaneous frequency of this sinusoid here into an amplitude at the output. Now let's look at how we can actually construct a frequency discriminator. So suppose that we have a differentiator followed by an envelope detector. Let's see if this system as a whole acts as a frequency discriminator. If the input to the differentiator is cosine of omega ct plus phi of t, then the output of the differentiator, which is also the input to the envelope detector, is ddt of cosine of omega ct plus phi of t, which equals minus sine of omega ct plus phi of t, times, by chain rule, the derivative of this here with respect to time, which is omega c plus d phi of t dt. Now, recall from Lab 2 that an envelope detector is a system that takes in general, I of t times cosine of omega ct and produces magnitude of I of t at the output. So if the output of the differentiator is fed to the input of the envelope detector, we have minus sine of omega ct plus phi of t times omega c plus d phi of t dt goes into the envelope detector, and at the output, we would get absolute value of minus omega c plus d phi of t dt, which equals omega c plus d phi of t dt, assuming that omega c plus d phi of t dt is greater than or equal to 0. Now, how does this actually discriminate frequencies? Well, if we assume that the phase phi of t of the input sinusoid isn't time varying, then the output is omega c itself. So cosine of omega ct plus phi goes through I frequency discriminator, and at the output, we get simply omega c. And based on this, if I input a sinusoid of a higher frequency to our composite system, then the output omega c, which is DC, would be higher. And conversely, if I input a sinusoid of a lower frequency, then the output would be lower. And so this way, the system output is proportional to the frequency of the input, and hence it acts as a frequency discriminator. Now, how is this actually done in practice? Well, the differentiator is an op-amp circuit with a capacitor and resistor R1 connected to the inverting terminal, and then a feedback resistor IF from the inverting terminal to the output, and then the non-inverting terminal is connected to ground. The envelope detector, as we saw in Lab 2, can be made by using a PN junction diode and then a resistor in parallel with a capacitor, and the output voltage is taken across the capacitor. So in this lab, you will build the differentiator and the envelope detector, and will then connect the wavegen input to the input of the differentiator, feed the output of the differentiator to the input of the envelope detector, and then measure the output voltage as the voltage across the capacitor in the envelope detector. All right, now how does this frequency discriminator relate to the main topic of the lab, which is implementing an FSK digital receiver and using that to decode a message? So over the past 50 years, there's been a transition from analog to digital communication systems. An analog communication system like AM radio, which you'll build in Lab 4, transmit an analog signal, so a signal that's continuous in time and continuous in amplitude, from the sender to the receiver. On the other hand, in a digital communication system, which is the focus of this lab, the values of the signal are discrete or quantized, and the time n is also discrete. If the signal can only take on one of two possible values, then each small piece of the digital signal is called a bit and is denoted by the binary digits 0 and 1. And digital communication systems have many advantages compared to analog ones, since nowadays much of the information we're trying to transmit is already in digital form. It's easy to store and process digital data. It's possible to detect and correct errors in digital communication in ways that would be impossible in analog communication. And multiple digital data streams can be easily multiplexed and sent together. And if you want to learn more about digital communication systems, you should take EECS 455. Now, just because a signal is analog doesn't mean that we can't transmit it digitally. As you'll learn towards the end of the semester, any analog signal can be converted into a digital signal by taking samples of the analog signal at uniformly spaced instants in time, and then converting the sample values into binary numbers through a process called quantization. Now, once a signal is in digital form, there's many different ways that can be used to transmit the digital data. And in this lab, we're going to use the method known as frequency shift keying, or abbreviated as FSK. In binary FSK, the data is transmitted as a sequence of tones or sinusoids, where each tone can have only one of two possible frequencies. The higher frequency tone will be assigned the binary digit 1, and the lower frequency tone will be assigned the binary digit 0. And so the audio file provided to you on Canvas has a message encoded in it, where that message is a base 10 number between 0 and 255. And this number has been converted into its corresponding 8-bit binary string. The computer will then transmit this 8-bit binary string using a sequence of 8 binary FSK sinusoids, each of 2-second duration. Now, since the string of 8 binary bits is encoded as a sequence of 8 sinusoidal tones, you're going to use your frequency discriminator circuit to convert each sinusoidal tone into an output signal that's proportional to the corresponding frequency of the tone. And so a plot of the output of the frequency discriminator circuit might look something like this. Since a lower output corresponds to the binary digit 0, and the higher output corresponds to the binary digit 1, you can write down the binary string encoded in the audio file, and from that, you can convert it to base 10 to obtain the actual message. So for instance, if this was the output of the envelope detector when I input the audio file into my frequency discriminator circuit, then I would write down 0 for the first tone, 1 for the second tone, 1 for the third tone, 0 for the fourth tone, 0 for the fifth tone, 1 for the sixth tone, 0 for the seventh tone, and 1 for the eighth tone. And then from that, you can convert this 8-bit binary string to base 10 and obtain the actual message.